What if everything we think we know about the universe is just the surface, a mere glimpse into something far stranger and more complex hiding just beyond our perception? Picture this: galaxies spinning faster than they should, stars moving in ways that defy gravity's known rules, and vast stretches of invisible matter bending the fabric of space itself. These aren't flaws in our understanding, they're clues, hints that the cosmos is whispering secrets about layers we've yet to uncover. For centuries, we've gazed at the night sky, believing we were decoding the universe's grand design. But what if the truth is far wilder? What if reality as we know it is just one thread in a tapestry of hidden dimensions, parallel worlds, and forces so alien they rewrite the rules of existence? That's where these 30 theories come in. Each one peels back another layer of the cosmic onion, revealing possibilities that range from the awe-inspiring to the downright terrifying. Imagine universes stacked like pages in a book, separated by membranes thinner than atoms. Picture time not as a straight line but as a branching river, splitting endlessly into alternate realities. Or consider the spine-chilling idea that our entire universe could be a hologram, a flawless illusion projected from the edges of space itself. These aren't science fiction. They're serious, cutting-edge ideas debated by physicists, astronomers, and philosophers, all scrambling to explain the gaps in our cosmic map. This video isn't just a tour of wild guesses, it's a journey into the frontiers of human curiosity. We'll explore how dark matter might be the ghostly residue of a second Big Bang, how black holes could be gateways to other dimensions, and why some scientists think entire civilizations might exist in shadows we can't see. By the end, you won't just question the universe, you'll wonder if we've even begun to scratch its surface. So buckle up, reality is about to get a lot weirder. What if everything you see, the trees, the stars, even your own hands, isn't truly three-dimensional at all? This is the startling premise of the Holographic Universe Principle, a theory that suggests our reality might be nothing more than an incredibly convincing projection, like a cosmic movie screen. Imagine the universe as a giant hologram, where every detail from the spin of a quark to the explosion of a supernova is encoded on a distant, two-dimensional surface, perhaps even at the edge of space-time itself. The idea sounds like something from a sci-fi novel, but it's rooted in some of the most profound puzzles of modern physics. The theory traces back to the work of physicist Leonard Susskind and others who discovered something bizarre about black holes. When matter falls into a black hole, it doesn't just vanish, it leaves behind an imprint of information on the event horizon, the point of no return. This revelation led to a radical thought. If information isn't lost but stored on a boundary, could the same be true for the entire universe? Just like the pixels on your phone screen create the illusion of depth, the cosmos might be a vast, intricate projection, with all the information needed to build reality written on some far-off, flat surface. Here's where it gets even stranger. The holographic principle doesn't just challenge our intuition, it could solve one of physics' biggest headaches, the conflict between quantum mechanics and gravity. Quantum theory governs the tiny world of particles, while Einstein's relativity shapes the cosmos at large. But when these two frameworks collide, the math breaks down. A holographic universe might bridge that gap, suggesting that gravity isn't fundamental but emerges from something deeper, like ripples on the surface of a pond. Think about a video game. The world you explore seems vast and three-dimensional, but in reality, it's all generated from code stored in a two-dimensional memory chip. The holographic universe proposes that reality might work the same way. If true, it would mean the stars, galaxies, and even your thoughts are just shadows of a deeper, hidden layer of the cosmos. And if that's not mind-bending enough, some scientists speculate that this principle could mean there are no true locations in space, just relationships between bits of information, like a cosmic game of connect the dots. So, are we living in a hologram? The answer might lie in the faintest whispers of the universe, the cosmic microwave background, the afterglow of the Big Bang. Some researchers have scoured this ancient light for patterns, hunting for tiny pixel-like distortions that could betray reality's true nature. So far, the evidence is inconclusive, but the very possibility forces us to ask, if the universe is a projection, what or who is holding the projector? The holographic universe might bend your perception of reality, but the multiverse theory could shatter it entirely. Imagine not just one universe, but an endless sea of them, each with its own laws of physics, its own versions of history, even alternate versions of you making different choices at every turn. This isn't fantasy, it's a serious scientific possibility born from two of the most powerful theories in physics. First, let's talk about the quantum side of things. According to the many worlds interpretation, every time a particle faces a choice like whether to spin left or right, the universe splits. One path continues here, while another branches off into a parallel timeline. Think of it like a choose-your-own-adventure book where every possible outcome happens, just in different worlds. You might have turned left at that traffic light today, but in another universe you turned right, and who knows how differently life unfolded there. Then there's the cosmological version, eternal inflation, which paints an even grander picture. Picture the Big Bang not as a one-time event, but as a never-ending fireworks show. Our universe is just one bubble in an infinite cosmic foam, endlessly expanding alongside countless others. Some of these bubbles might have stronger gravity, weaker light, or even entirely different dimensions. Others could be nearly identical to ours, with only the tiniest variations, like a world where dinosaurs never went extinct, or where your favorite movie had a different ending. To grasp the scale, imagine blowing soap bubbles in a park. Each one floats independently, unaware of the others. Now, imagine that park is infinite and the bubbles never pop. That's the multiverse, an unending froth of realities, some similar, some unimaginably alien. Some physicists even speculate that collisions between these bubble universes might leave scars in our cosmic microwave background, ghostly fingerprints of other worlds bumping into ours. But why believe in something so extravagant? Because it solves puzzles. Quantum mechanics gives us math that only makes sense if every possible outcome happens somewhere. Eternal inflation explains why our universe's constants, like the strength of gravity, seem eerily fine-tuned for life. If there are infinite universes, it's no surprise we find ourselves in one where conditions are just right. Of course, not everyone's convinced. Critics argue the multiverse is untestable, more philosophy than science. Yet others counter that evidence might lurk in gravitational waves or quantum experiments. Whether real or not, the multiverse forces us to confront a humbling thought. We might not just be insignificant in space, but in an infinite ocean of time and possibility. So the next time you make a choice, remember, somewhere out there, another version of you might have chosen differently, and that's just the beginning. We've all heard about dark matter, the mysterious, invisible glue holding galaxies together, making up most of the universe's mass yet refusing to interact with light. But what if it's not just some exotic particle? What if dark matter is something far stranger, ordinary matter from a parallel universe brushing against ours through hidden dimensions? This isn't just a wild thought experiment. It's a serious hypothesis gaining traction thanks to researchers at Durham University and beyond. Here's the idea. Picture two soap bubbles floating side by side, nearly touching but not quite. Now imagine those bubbles are entire universes, separated by a higher dimension we can't perceive. In one bubble, that's us, our stars, our planets, the light we see. In the other, another cosmos with its own stars and galaxies, made of the same familiar protons, electrons, and atoms. Normally, these universes wouldn't interfere with each other, but gravity, unlike other forces, might be able to seep through the membrane between them. That faint gravitational tug could be what we've been calling dark matter all along, not an undiscovered particle, but the ghostly pull of another reality bleeding into ours. The math behind this is surprisingly elegant. In our universe, gravity appears weak compared to other forces, but if it's actually leaking into higher dimensions or neighboring universes, that could explain why. Think of it like a flashlight shining through a curtain. Most of the light stays on one side, but a faint glow slips through. Similarly, most of the parallel universe's gravity stays there, but a fraction leaks out, manifesting as the gravitational effects we attribute to dark matter. Durham University's team took this concept further. They simulated how galaxies would behave if dark matter were really the gravity of a mirror universe. The results astonishingly close to what we observe in the real cosmos. Galaxies spun at the right speeds, clusters formed the correct shapes, all without needing to invent new particles. It's as if the universe handed us a riddle, and the answer might be hiding in plain sight, just in another dimension. Of course, this raises spine-tingling questions. If gravity can leak between universes, could there be regions where these realities briefly overlap, creating anomalies in space or time? Some theorists speculate that certain cosmic oddities, like galaxies moving in unison across vast distances, might be fingerprints of such intersections. And if another universe is truly out there, mirroring ours, does that mean it also has life, intelligence, even versions of us? Skeptics argue we're far from proving any of this. Detecting a parallel universe's gravity directly would require breakthroughs we can barely imagine. But the beauty of science is its willingness to chase even the wildest ideas. After all, dark matter was once considered fringe. Now it's textbook. Whether this theory holds up or not, it forces us to rethink the boundaries of reality and wonder just how much of the cosmos remains hidden in plain sight. What if every moment of your life, the warmth of sunlight, the sound of laughter, even the weight of this question in your mind, was nothing more than lines of code in an unfathomably advanced simulation? This is the core of Nick Bostrom's simulation argument, a trilemma that forces us to confront three unsettling possibilities about reality. Either civilizations like ours almost always go extinct before reaching technological maturity. They choose not to run ancestor simulations of their past, or we're almost certainly living in one right now. No matter which option you pick, the implications are staggering. Let's break it down. Bostrom, a philosopher at Oxford, argues that if a civilization could one day create simulations indistinguishable from reality, populated with conscious beings like us, then the number of simulated minds would vastly outnumber biological ones. Think of it like video game characters. If future humans built billions of virtual worlds, the odds that we're in the original base reality shrink to near zero. It's like realizing you're probably not the first person to shuffle a deck of cards statistically. You're somewhere in the middle of an endless sequence. But how could a simulation fool us so completely? Start with the quantum world. At the tiniest scales, particles behave in ways that seem almost pixelated, as if the universe has a resolution limit. Even space-time itself might be quantized, broken into indivisible Planck-length units, like the dots on a newspaper photo that merge into an image when you step back. Some physicists speculate this graininess isn't just nature's quirk, but a sign of computational constraints, the universe's way of conserving processing power. Then there are the potential glitches. If reality were a simulation, occasional bugs might betray its engineered nature. Ever experienced déjà vu, that eerie sense you've lived a moment before? Some joke it's a memory leak in the cosmic code. More seriously, scientists have searched for anomalies in high-energy particle collisions or patterns in cosmic rays that might hint at underlying programming rules. Others point to quantum entanglement, where particles instantly influence each other across vast distances, as potential evidence of lazy rendering, where the simulation only calculates linked states when observed, saving resources. But the most chilling idea, if we're in a simulation, the creators could intervene at any moment. Ancient myths of gods, modern UFO sightings, even inexplicable miracles. Could these be moments when the programmers tweak the parameters or worse, decide to shut the experiment down? The simulation argument doesn't just question what's real, it turns existence itself into the ultimate cosmic mystery. And if it's true, the next question is even more haunting: who's running the simulation and why? The Big Bang isn't the only way the universe could have begun. Imagine instead a cosmic collision, two immense parallel worlds slamming together in a higher dimensional space, igniting not with a singularity but with a fiery rebirth. This is the heart of the ekpyrotic universe theory, a radical alternative that rewrites the origin story of everything. Instead of exploding from a single point, our cosmos might be one of countless membranes, or brains, floating in a vast, unseen dimension, periodically crashing into a neighboring brain like sheets of paper slapped together. Each collision would release enough energy to reboot reality, creating what we perceive as a Big Bang without the need for infinite density or the breakdown of physics. The idea builds on string theory's wildest implications. In this framework, our three-dimensional universe could be a brain drifting through a higher dimensional bulk. Picture a loaf of bread where each slice is a separate universe, hovering millimeters apart in a dimension we can't perceive. Normally, these brains don't interact. But if they're drawn together by some unseen force, perhaps a form of cosmic gravity, their collision would unleash titanic energy, heating empty space to trillions of degrees and flooding it with particles. This isn't destruction, it's transformation, a cycle of cosmic renewal where each crash resets the clock. What makes this model so compelling is how neatly it sidesteps the Big Bang's biggest puzzles. Traditional cosmology struggles with the singularity problem, the moment when all matter and energy were crushed into an infinitely dense point where physics ceases to make sense. The ekpyrotic universe avoids this entirely. No infinites, no breakdowns, just two brains bouncing apart after impact, their energy gradually cooling into galaxies, stars, and us. Even the universe's remarkable uniformity, the fact that the cosmic microwave background looks eerily similar in all directions, finds an elegant explanation. Before the collision, the brains could have been stretched smooth over eons, like dough rolled flat, ensuring the resulting universe started with perfect symmetry. But there's a twist. If this theory is true, our universe might not be the only one cycling through these collisions. Other brain pairs could be out there, crashing in their own higher dimensional voids, each creating separate cosmic timelines. Some might have slightly different physical constants, leading to universes where gravity is stronger, light slower, or chemistry impossible. It's a multiverse, but not the quantum or inflationary kind. Instead, it's a multiverse of clashing membranes, each collision writing a new chapter in an endless cosmic saga. The echoes of these ancient collisions might still linger. Some theorists suggest that gravitational waves, ripples in space-time, from the last brain smash could be hiding in the universe's oldest light, waiting to be detected. Others speculate that if brains are warped or wrinkled, their collisions might not be perfectly uniform, leaving subtle scars in the distribution of galaxies or the fabric of space itself. Finding such fingerprints wouldn't just prove the theory, it would redefine our place in the cosmos. We wouldn't be the aftermath of a single explosion, but the latest iteration in an infinite cycle, destined to collide, reboot, and begin again. Of course, skeptics argue that higher dimensions and colliding brains are untestable speculation. Yet the same was once said about black holes and the Big Bang. Whether the ekpyrotic universe holds up or not, it forces us to confront a profound possibility. The birth of our universe might not have been a beginning at all, but a moment in an endless cosmic dance, one where the music never stops and the dancers are entire realities, forever moving toward their next collision. We think of time as an unstoppable river always flowing forward, carving history into past, present, and future. But what if that's just a trick of the mind? Physicist Julian Barber proposes something far stranger. Time might not exist at all as a fundamental force. Instead, our entire experience of moments passing could be an illusion, emerging from something deeper, a cosmic tapestry of quantum relationships where every now exists simultaneously, like frames in a film reel waiting to be projected. Barber's radical idea begins with a simple but profound observation. When we measure time, whether with atomic clocks or celestial motions, we're always tracking change. The swing of a pendulum, the vibration of a cesium atom, Earth's orbit around the Sun. Without these physical processes, time has no meaning. So what if time isn't a backdrop to the universe, but a side effect of how objects interact? Picture a vast, frozen landscape where every possible configuration of particles exists at once, static and unchanging. Our sense of movement comes from jumping between these configurations, like flipping through a stack of snapshots. Each moment is complete in itself, and time is just the thread we weave between them. This aligns eerily well with quantum mechanics, where particles exist in superpositions, multiple states at once, until observation collapses them into a single outcome. In Barber's timeless universe, every possible quantum state exists eternally, and what we call time's flow is just our limited perspective, hopping from one state to the next. Think of it like reading a novel. The story feels alive as you turn the pages, but the entire book already exists, complete from first word to last. Similarly, the universe might be a finished block where past, present, and future are equally real. We're just tracing a single path through it. The implications are staggering. If time isn't fundamental, then concepts like cause and effect, aging, even entropy might be emergent phenomena, like waves rising from a still ocean. Barber's math suggests reality could be a network of nows called time capsules, self-contained configurations that create the illusion of sequence. Our brains stitch these moments together, constructing a narrative of continuity from what's actually a series of quantum jumps. Critics argue this undermines our intuitive understanding of change. How does evolution occur or memories form without genuine progression? Barber counters that these phenomena are just patterns in the cosmic data, like constellations in the night sky, meaningful only from a certain viewpoint. Even more mind-bending, if time is emergent, then the arrow of time, why we remember the past but not the future, could be a quirk of how our particular slice of the universe is structured. Other configurations might a LLOW Chinese letter experience flowing backward. So why does time feel so real? The answer might lie in complexity. Simple systems like two orbiting planets can be described without time, but conscious observers like us require intricate interactions to exist. Our perception of time could be the brain's way of making sense of these layered quantum relationships, turning static snapshots into a dynamic story. Experiments are probing these ideas. Quantum gravity researchers are studying timeless formulations of physics, while others hunt for signatures of a fundamental, timeless layer in cosmic data. If Barber's right, the consequences would rewrite not just physics but philosophy itself. Free will, identity, even mortality, all might be illusions spun from a timeless cosmos where every now is forever. The past isn't gone, the future isn't unwritten. They're just pages we haven't turned to yet. Black holes have always been cosmic enigmas, regions where gravity is so intense that not even light can escape. But what if these gravitational monsters aren't just destructive forces? What if each one is the seed of an entirely new universe, hidden behind its event horizon like a cosmic matryoshka doll? This is the spine-tingling premise of the black hole universe theory, which suggests our entire cosmos might have been born inside a black hole from a parent universe, making the Big Bang not a beginning but a rebirth. At first glance, the idea seems outrageous. Black holes crush matter into oblivion, right, yet dig deeper, and the math tells a different story. When matter collapses into a singularity, the equations of general relativity break down, signaling not an end but a transition, a point where our understanding of space and time dissolves. Some physicists, like Nikodem Poplawski, propose that inside this singularity, conditions might be so extreme that space-time flips inside out. Instead of collapsing forever, the infalling matter could rebound in a white hole, a theoretical opposite of a black hole that spews out energy rather than trapping it. This explosive rebound could look remarkably like the Big Bang from our perspective, birthing a new universe with its own physical laws, tucked safely inside the black hole that spawned it. Here's where it gets even wilder. If our universe exists within a black hole, the parent universe's gravity could still influence us, not as a force we recognize, but as the mysterious dark energy accelerating the expansion of our cosmos. Dark energy, which makes up 68% of the universe's energy budget, could be the faint gravitational echo of the outside universe pressing inward, stretching our space-time in ways we misinterpret as expansion. Imagine blowing up a balloon inside another balloon. The inner balloon's growth might feel like expansion from its own perspective, but it's also responding to the pressure of the outer one. The theory also elegantly explains why our universe appears finely tuned for life. If black holes naturally spawn new universes, then those with constants conducive to structure, like ours, would be the ones where stars, planets, and ultimately observers like us could arise. In this cosmic Darwinism, universes with successful physics replicate endlessly through black holes, while inhospitable ones vanish without progeny. It's a mind-bending twist on the multiverse idea, where survival of the fittest applies not to life but to entire realities. Could we ever prove this? Some researchers suggest looking for anomalies in the cosmic microwave background, subtle imprints left by the black hole's formation. Others propose that the universe's overall rotation, if it spins in sync with its parent black hole, might betray its origins. Even more unsettling, if this theory holds, black holes in our universe might themselves be budding new cosmos, meaning we could be standing atop an infinite fractal of nested realities, each unaware of the others. The black hole universe theory forces us to reconsider not just our place in the cosmos, but the nature of existence itself. Are we the product of a cosmic accident, or the latest iteration in an endless cycle of universes birthing universes? Whether true or not, the idea reshapes black holes from apocalyptic endpoints into something far more profound: cosmic wombs, cradling new realities in their depths. And if that's the case, the night sky isn't just a window to the stars. It might be a mirror reflecting the infinite layers of creation itself. What if your thoughts aren't just a product of your brain, but a fundamental force shaping reality itself? This is the startling premise of quantum consciousness, a theory that bridges the gap between mind and matter by suggesting consciousness isn't merely a passive observer but an active participant in the universe's quantum dance. At the heart of this idea lies a radical reimagining of how we perceive existence, where the very act of observation could be weaving the fabric of reality. One of the most provocative takes on this comes from physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff, who proposed the orchestrated objective reduction theory, ORCH for short. They argue that consciousness arises from quantum processes happening inside the brain's microtubules, tiny protein structures that form the skeleton of neurons. These microtubules aren't just cellular scaffolding. According to ORCH, they're quantum computers, processing information at scales so small they flirt with the fuzzy boundaries of quantum mechanics. When these quantum states collapse, a process Penrose ties to gravity's subtle tug. They generate moments of conscious awareness, like pixels lighting up to form an image. The implications are staggering. If consciousness stems from quantum phenomena, It might explain why our observations seem to influence quantum systems, like in the famous double-slit experiment, where particles behave as waves until measured, then choose a definite state. Some interpretations suggest this collapse isn't random but guided by conscious observation, meaning the universe doesn't fully exist until a mind interacts with it. Imagine a tree falling in a forest with no one around. In this view, it wouldn't make a sound or even fully exist until observed. Experiments have added fuel to the fire. Studies on anesthetic gases show they disrupt microtubule function, eerily paralleling how they switch off consciousness. Other research hints that certain brain processes might exploit quantum coherence, the same phenomenon that lets particles exist in multiple states at once. Even photosynthesis, a process far older than human brains, relies on quantum effects to harvest sunlight with near-perfect efficiency. Could nature have been using quantum mechanics to bridge mind and matter long before we noticed? Critics dismiss or as speculative, pointing out the warm, noisy environment of the brain seems hostile to delicate quantum states. Yet proponents counter that microtubules might be shielded, like quantum computers cooled to near absolute zero. Others argue consciousness could emerge from classical physics alone, no quantum weirdness required. But the theory's boldest claim lingers: if consciousness shapes reality, then the universe might not be a cold, indifferent machine but a participatory cosmos, where mind and matter are entwined at the deepest level. This isn't just philosophy, it's a challenge to rethink everything from artificial intelligence to the nature of existence. If consciousness is quantum, could machines ever truly think, or would they lack this fundamental link to reality's fabric? And if observation creates reality, what does that say about the universe before life emerged? Was it a haze of possibilities, waiting for the first mind to crystallize it into being? Quantum consciousness doesn't just blur the line between observer and observed, it erases it entirely, suggesting we're not just inhabitants of the cosmos but its co-creators. Dark energy isn't just expanding the universe, it might be tearing it apart. Picture this: galaxies drifting farther away, stars fading into isolation, and eventually, planets, molecules, even atoms themselves ripped to shreds as the very fabric of space-time stretches beyond its limits. This isn't science fiction, it's the Big Rip, one of the most chilling fates proposed for our cosmos. And at the heart of this apocalyptic scenario lies a mysterious force known as a scalar field, an invisible energy permeating the universe, pushing it toward disintegration. The story starts with dark energy, which makes up about 68% of the universe's energy budget. For decades, we've known it's accelerating the expansion of space, but what if its influence isn't constant? Some theories suggest dark energy could be a dynamic scalar field, a kind of cosmic fluid with pressure so negative it grows stronger over time. Unlike gravity, which pulls things together, this phantom energy would do the opposite: its repulsive force intensifying until not even atomic bonds can withstand it. Here's how the Big Rip unfolds. First, galaxies beyond our local group vanish over the cosmological horizon, their light stretched beyond detectability. Then gravity loses its grip, tearing apart galaxy clusters, then individual galaxies. As the phantom field's strength grows, it overpowers the forces holding stars together, reducing them to scattered gas. Planets are next, ripped from their orbits. In the final moments, even atomic nuclei, the building blocks of matter, are torn apart, leaving a universe of solitary particles unable to interact. Time and space cease to have meaning in a reality where nothing can hold itself together. The timeline depends on the scalar field's properties. If dark energy's equation of state crosses a critical threshold, a value called W equals -1, the Big Rip becomes inevitable. Current estimates suggest it could happen in as little as 22 billion years. That might sound distant, but on cosmic scales, it's a blink of an eye. For context, Earth's final sunset would come long before the rip, our planet torn apart roughly 30 minutes before the end. What makes this theory especially haunting is that it inverts our intuition about the universe's fate. Instead of a slow heat death where everything fades into cold darkness, the Big Rip is violent and abrupt, a cosmic crescendo of destruction. Some models even suggest that as space-time stretches thin, quantum fluctuations could spawn new universes in the wreckage, turning the end of one cosmos into the birth of another. Yet the Big Rip isn't the only possibility. Alternative theories propose that dark energy could decay or transition into something benign, sparing the universe from dissolution. Others argue that phantom energy violates thermodynamic laws, making the scenario impossible. But until we understand dark energy's true nature, the specter of the Rip lingers, a reminder that the universe's expansion isn't just carrying galaxies away from us, but possibly hurtling everything toward an unimaginable end. The search for answers lies in the cosmos itself. By mapping the universe's expansion with unprecedented precision through projects like the Dark Energy Spectroscopic Instrument, we might detect subtle shifts in dark energy's behavior, hints that it's evolving into something more destructive. For now, the Big Rip remains a hypothesis, but its implications force us to confront a profound truth. The universe's fate might not be written in stars, but in the invisible, unfathomable energy hiding in the empty spaces between them. Among all the bizarre possibilities lurking in the frontiers of physics, few are as unsettling as the Boltzmann brain paradox. It begins with a simple but profound question. If the universe tends toward disorder over time, why does our reality contain so much structure, planets, stars, and conscious minds like ours? The answer might force us to confront a terrifying possibility that you, the observer contemplating these words right now, are far more likely to be a momentary flicker of self-awareness conjured by random quantum fluctuations than a product of 13.8 billion years of cosmic evolution. The paradox traces back to 19th century physicist Ludwig Boltzmann, who grappled with entropy, the tendency of systems to descend into chaos. In an infinitely old universe, he reasoned, even the most improbable states must occasionally arise purely by chance. Given enough time, atoms jostling randomly could spontaneously arrange into a fully formed brain, complete with fabricated memories of a life that never actually happened. Statistically, such an event would be unimaginably rare, but in an eternal cosmos, rare events become inevitable. The unsettling twist: a single, isolated brain blinking into existence requires vastly less energy and organization than an entire orderly universe. So if reality truly is random and eternal, Boltzmann brains should outnumber real observers like us by an astronomical margin. This isn't just abstract theorizing. Modern cosmology amplifies the paradox. If dark energy keeps stretching spacetime forever, our universe will eventually reach heat death, a featureless void where all energy is evenly dispersed. Yet quantum mechanics dictates that even in perfect emptiness, particles can briefly pop into existence due to uncertainty. Over trillions upon trillions of years, these fluctuations could assemble conscious minds out of nothingness, complete with elaborate but entirely false perceptions of reality. You might wake up as one of these minds with fabricated memories of reading this sentence, only to dissolve back into the void nanoseconds later. The implications shatter our trust in reality itself. If Boltzmann brains dominate the cosmos, then all scientific evidence from fossil records to cosmic microwave background could be illusions generated in a transient mind. Even the memory of testing this hypothesis might be fabricated. Some physicists dismiss the paradox as a reductio ad absurdum proof that our assumptions about the universe's eternity or randomness must be flawed. Others propose solutions like the idea that quantum gravity prevents such fluctuations, or that universes with observers like us are more probable due to undiscovered laws. Yet the Boltzmann brain endures as cosmology's ultimate skeptic's argument, whispering that all we perceive, every galaxy, every law of physics, even the passage of time might be nothing more than a mirage in the mind of a phantom. Whether a thought experiment or a genuine crisis for physics, it forces us to ask, how do we know anything at all? What if space-time itself isn't smooth and continuous, but built from tiny, indivisible building blocks like atoms of geometry? This is the radical idea behind the crystalline universe theory, which suggests that at the smallest possible scales, the fabric of reality might resemble an intricate quantum crystal, its lattice structure dictating the rules of physics itself. While we experience space and time as fluid and seamless, down at the Planck length, a scale so small it's a trillion times tinier than an atom, the universe could be pixelated, with each pixel a fixed unit of space-time locked into an orderly, repeating pattern. The theory emerges from a deep tension in modern physics. Quantum mechanics governs the tiny world of particles, where everything is discrete and quantized energy comes in packets, light in photons. Yet general relativity describes space-time as a smooth, deformable fabric, bending under gravity's influence. These two frameworks refuse to reconcile, creating mathematical chaos when forced together. But if space-time has a crystalline structure at its foundation, the paradox might dissolve. Imagine a grid so fine it's imperceptible in everyday life, like the pixels on a high-resolution screen. From a distance, the image looks smooth, but zoom in far enough, and you'll see the discrete tiles that compose it. In this view, the smooth curvature of space-time in relativity would be an illusion, emerging from the collective behavior of these microscopic geometric units, just as the rigidity of a diamond emerges from the precise alignment of its atoms. This isn't just poetic speculation. Certain quantum gravity approaches, like loop quantum gravity, already treat space-time as a network of interconnected loops or spins, akin to a cosmic mesh. The crystalline theory takes this further, proposing that these loops arrange into a lattice with symmetries that could explain fundamental forces. For instance, distortions or defects in the space-time crystal might manifest as particles. An electron could be a twist in the lattice, a photon a ripple propagating through it. Even gravity might emerge from the collective flexing of this structure, like sound waves traveling through a solid. One startling implication: the speed of light might not be a fundamental constant, but a property of the crystal structure, just as the speed of sound depends on the material it travels through. If the space-time lattice vibrates or evolves, light's speed could have been different in the early universe, potentially explaining cosmic anomalies like the horizon problem. Some models even suggest that high-energy particles like cosmic rays could feel the graininess of space-time, deviating slightly from expected paths, a faint fingerprint of the universe's hidden architecture. Critics argue that such discreteness would violate Lorentz symmetry, a cornerstone of relativity, stating that physics works the same no matter your velocity or direction. But proponents counter that the effect would be vanishingly small at everyday energies, hidden from current experiments. Others worry that a crystalline universe might reintroduce absolute space and time concepts Einstein dismantled. Yet if the theory holds, it could rewrite our understanding of existence, turning space-time from an abstract stage into something tangible, with structure, defects, and perhaps even the potential to engineer it. The hunt for evidence is on. Scientists are probing ultra-high-energy cosmic rays and quantum optics experiments for signs of spacetime's graininess. Others are simulating crystalline spacetime on supercomputers, watching how virtual universes evolve under these rules. If the crystalline universe is real, we're not just living in space, we're inside an unimaginably vast dynamic crystal, whose hidden geometry orchestrates everything from the orbit of planets to the flicker of thought in your mind. And that raises a tantalizing question. If space-time has a structure, could it ever be broken or reshaped? The universe doesn't just contain life, it might be alive. Not in the way we think of biological organisms, but as a vast, self-organizing system where galaxies act like neural networks and dark matter flows like a cosmic circulatory system. This is the living universe hypothesis, a mind-bending idea that reshapes reality from a cold, mechanical void into something eerily resembling a conscious entity. At its core, it's an expansion of the Gaia principle, the notion that Earth functions as a single, self-regulating system but scaled up to cosmic proportions. Imagine the universe not as a random scattering of stars, but as a dynamic, interconnected web where every supercluster and black hole plays a role in some grand, unfolding process we're only beginning to glimpse. One striking parallel lies in the structure of galaxies and neurons. Under a microscope, the branching filaments of a human brain cell look uncannily like the tendrils of dark matter connecting galaxies across the cosmos. Both systems follow similar patterns of nodes and linkages, optimized for efficiency in transmitting information, whether it's electrical signals in a brain or gravitational influences across space-time. Some researchers argue this isn't just coincidence but evidence of universal scaling laws, where nature repeats the same blueprints at vastly different levels. If consciousness emerges from networked neurons, could the universe's large-scale structure hint at a deeper, cosmic-scale awareness? The idea gains traction when examining how galaxies self-regulate. Stars aren't born at random. Their formation is tightly controlled by feedback loops. Supernova explosions seed clouds of gas with heavy elements, triggering new star births while also dispersing material to prevent unchecked growth. It's a balancing act reminiscent of homeostasis in living organisms, the way your body regulates temperature or blood sugar. Even black holes, often seen as destructive forces, act like cosmic pacemakers, their jets injecting energy into galaxies to stabilize star formation rates. These processes suggest a universe that doesn't just evolve chaotically but adjusts, as if guided by an invisible hand. Perhaps the most provocative twist comes from quantum biology. We now know living organisms exploit quantum effects like photosynthesis, harnessing wave-particle duality to optimize energy transfer. If quantum processes bridge life and physics on Earth, could they also operate cosmically? Dark energy's acceleration might mirror cellular growth, while vacuum fluctuations, the quantum froth of empty space, could resemble metabolic activity at the universe's smallest scales. Even time's arrow might fit this framework, the universe's expansion driving complexity, much like evolution drives life toward greater organization. Critics dismiss this as poetic metaphor, arguing that self-organization doesn't imply consciousness. Yet proponents counter that we've underestimated nature's capacity for emergent intelligence before. Ant colonies exhibit swarm logic without central control. Slime molds solve mazes despite lacking brains. If simple systems can display problem-solving behaviors, why not the universe itself? Some mathematical models even suggest cosmic structures process information in ways that, while alien to our experience, might qualify as a form of computation. The implications spiral outward. If the universe is alive, its goals, if it has any, would be incomprehensible to us, unfolding over billions of years. Are black holes its memory storage? Is dark energy its growth mechanism? And if the cosmos is truly self-aware, does it perceive us at all, or are we mere transient fluctuations in its vast metabolism? The living universe hypothesis doesn't just challenge what reality is, it redefines our place within it. We might not be inhabitants of a dead cosmos, but cells in a body whose true nature remains just beyond our grasp. What if the universe isn't made of matter or energy at all, but of something far more fundamental: information? This is the radical proposition at the heart of the it-from-bit theory, where every particle, every force, even space-time itself, might be nothing more than bits of data in a cosmic computation. The idea stretches back to physicist John Archibald Wheeler, who famously suggested that reality could be built not from tangible stuff, but from answers to yes or no questions, binary choices woven into the fabric of existence itself. Imagine the cosmos as an unimaginably vast quantum computer, where what we perceive as stars, planets, and even our own thoughts are just intricate patterns of information flickering into being. This perspective finds startling support in quantum mechanics, where particles behave less like solid objects and more like packets of probability, their properties undefined until measured. The double-slit experiment, for instance, shows particles existing in multiple states at once until observation chooses one outcome. In the information universe view, this isn't a quirk but a clue. The act of measurement isn't just revealing reality, it's creating it by selecting from a menu of possible data points. Even entanglement, where particles instantaneously influence each other across vast distances, makes eerie sense if they're not separate entities but linked nodes in a network of shared information. Black holes offer the most dramatic evidence for this paradigm. When matter falls into a black hole, it vanishes from our universe, seemingly violating the principle that information can't be destroyed. But quantum theory insists information must persist, so where does it go? The holographic principle provides a jaw-dropping answer. All the information about what fell in gets encoded on the black hole's event horizon, the surface of its point of no return. Picture throwing a book into a fire. The pages burn, but if the smoke swirls somehow preserved every word, the information wouldn't be lost, just transformed. Similarly, a black hole's horizon might store data in Planck-sized pixels, like a cosmic hard drive, with each bit corresponding to an area 1 billion times smaller than a proton. This isn't just theoretical sleight of hand. In 2012, physicists fired lasers at entangled photons, simulating how information might scramble on a black hole's surface, and the math held up. Even more compelling, calculations show the entropy, a measure of information inside any space, is proportional not to its volume, but to the area of its boundary. It's as if the universe is a hologram with three-dimensional reality projecting from a two-dimensional dataset. The implications rewrite our understanding of existence. If information is foundational, then black holes aren't just cosmic trash compactors, they're the universe's most efficient information processors. The Big Bang might not have been an explosion of matter, but a burst of data initialization, like booting up a simulation. Even time could emerge from quantum computations, with each moment a new frame in a cosmic render. Skeptics argue this reduces reality to abstract math, but proponents counter that math might be all there is, a universe where the answers come before the questions, and everything, from the spin of an electron to the fate of galaxies, is just information waiting to be read. So where does that leave us? Perhaps as transient patterns in the data, fleeting configurations in an eternal computation. Or maybe as something more, participants in a universe where observation doesn't just record reality, but continuously builds it one bit at a time. Either way, the information universe doesn't just change what we think the cosmos is made of. It changes what it means to exist at all. Electric currents course through the cosmos on scales so vast they could wrap around galaxies, yet most astronomy textbooks barely mention them. This is the cornerstone of the electric universe theory, a radical reimagining of how the universe works that swaps gravity's dominance for the raw power of plasma and electromagnetism. Forget the serene, clockwork heavens of traditional cosmology. Picture instead a dynamic, crackling web of charged particles sculpting stars, birthing galaxies, and even carving the surfaces of planets, all through forces we can replicate in laboratory plasma chambers here on Earth. At its heart, the theory challenges one of modern astrophysics' sacred cows, that gravity alone shaped the cosmic large-scale structure. Proponents point to the uncanny resemblance between galaxy spirals and the intricate filaments seen in plasma discharge experiments, those shimmering, fractal tendrils that form when high-voltage electricity punches through ionized gas. In labs, these plasmas self-organize into twisting pinwheels, hourglass shapes, even perfect spirals, all without gravity's influence. Now zoom out. galaxies exhibit eerily similar forms, with arms that glow not just from starlight but from synchrotron radiation, a telltale signature of electrons spiraling in magnetic fields. Could these structures be less about dark matter's invisible pull and more about billion light-year-long circuits of electric current? The evidence mounts when you examine cosmic oddities. Take Jupiter's moon Io, peppered with volcanoes spewing sulfur hundreds of kilometers high. Mainstream models attribute this to tidal heating, but electric universe theorists highlight something peculiar. Io's eruptions often align with electrical flux tubes connecting it to Jupiter, a dynamic mirrored in plasma tubes that form between charged electrodes. Or consider spiral galaxies' barred centers. Lab plasmas under intense current naturally develop dense, linear central columns, precisely where galactic bars appear. Even the famous pillars of creation in the Eagle Nebula might not be passive gas clouds eroded by starlight, but active plasma formations called Z-pinches, where magnetic forces compress ionized matter into towering structures. Critics dismiss these parallels as coincidence, arguing that cosmic-scale currents would require impossibly high conductivity in near-perfect vacuums. But plasma cosmologists counter that space isn't truly empty. It's a dark current sea of low-density plasma, with even one charged particle per cubic meter enough to sustain galaxy-spanning circuits. They point to the galactic power problem. Many galaxies radiate far more energy than their stars can produce, yet their cores exhibit voltages matching predictions for colossal electromagnetic dynamos. Some galaxies even eject jets aligned with their spin axes, behavior perfectly mimicked by plasma-focused devices in labs, where charged particles spiral along magnetic fields before launching into narrow beams. Perhaps the most provocative claim concerns redshift, the stretching of light that supposedly proves the universe is expanding. Electric Universe advocates argue it could instead stem from electrons losing energy as they traverse intergalactic plasma, mimicking expansion without the need for dark energy or a Big Bang. If true, the cosmic microwave background might not be ancient afterglow but the glow of current-carrying plasma pervading space, a notion that would rewrite cosmology's origin story entirely. Of course, the mainstream remains skeptical. Without direct detection of galaxy-scale currents or a viable mechanism to replace general relativity's gravitational framework, the electric universe sits at the fringe. Yet its proponents urge us not to dismiss the patterns. When lab plasmas and deep space structures evolve identically under electromagnetic forces, shouldn't we at least ask if we've been reading the cosmos in the wrong language? Whether the theory holds or not, it sparks a vital question. Have we underestimated the electric crackle threading through the dark? The cosmos might not have a single beginning or end. Instead, it could be locked in an endless cycle of rebirths, where each universe is both the successor and predecessor of the next. This is the essence of Roger Penrose's conformal cyclic cosmology, a theory so audacious it rewrites time itself. Imagine a universe not with one big bang, but with countless big crunches and big bounces, where the death of one eon seeds the birth of another through a process so subtle it hides in plain sight within the oldest light we can see. At first glance, the idea seems to defy physics. How could a universe that's expanded into near nothingness, its black holes evaporated, its particles decayed to faint radiation, somehow reset into a new fiery beginning? Penrose's answer lies in a mathematical sleight of hand called conformal rescaling. As a universe approaches heat death, all distances stretch toward infinity, and all particles lose their mass due to quantum effects. In this state, the cosmos becomes effectively timeless and scale-free, a blank canvas where the end of one epoch can geometrically match the hot, dense start of another. It's like taking an infinitely stretched rubber band and snapping it back to its original form without losing its essential properties. The transition isn't explosive, it's a seamless metamorphosis where the end curves back into a beginning. But how do we test such a mind-bending idea? Penrose and his collaborators turned to the cosmic microwave background, the afterglow of the Big Bang. If previous eons left faint imprints, they might linger as anomalous rings or swirls in this ancient light. In 2010, Penrose claimed to have found just that, concentric circles in the CMB where temperatures varied unexpectedly, which he interpreted as gravitational shockwaves from black hole collisions in a prior universe. These Hawking points, named after Stephen Hawking's prediction that evaporating black holes would release bursts of energy, could be cosmic fossils, echoes of a universe that existed before our own. The implications for black holes are equally startling. In conformal cyclic cosmology, these gravitational monsters don't just vanish, their evaporation seeds the next eon. As a black hole loses mass through Hawking radiation, its information isn't destroyed but imprinted onto the boundary of the new universe, like a message pressed into wet clay. Over unimaginable eons, all black holes dissolve, their energy spreading uniformly, and this uniform haze becomes the raw material for the next Big Bang. In this way, black holes aren't endpoints but cosmic recyclers, transforming the debris of one epoch into the fuel for the next. Critics argue that the CMB anomalies Penrose identified could be statistical flukes or artifacts of data processing. Others question whether conformal rescaling truly bridges the thermodynamic gap between a cold, dead universe and a hot, dense one. Yet the theory's elegance is undeniable. It solves the mystery of why our universe began in such a low entropy state, a nagging puzzle in cosmology by suggesting that the beginning was actually a continuation, a resetting of the clock by natural law. If Penrose is right, our universe is just one page in an infinite cosmic ledger, each chapter written with the ashes of the last. The stars we see at night, the planets we call home, even the atoms in our bodies might be stardust from a forgotten eon, destined to dissolve and rise again in a cycle without end. It's a vision both humbling and hopeful, a universe where nothing is truly lost, only transformed forever. Look closely at a spiral galaxy's swirling arms, then zoom way in, to the branching veins of a leaf or the jagged coastline of a continent. At first glance, they share nothing in common, yet mathematically their patterns echo one another with uncanny precision. This isn't coincidence, it's the signature of a fractal universe, a cosmos where the same intricate shapes repeat at every scale, from the quantum foam to the vast cosmic web. The man who first decoded this hidden order, mathematician Benoit Mandelbrot, didn't set out to revolutionize cosmology. He was studying stock market fluctuations and cotton price trends when he noticed something peculiar. Chaos had a hidden geometry. Whether plotting financial data or measuring the length of England's coastline, certain patterns reappeared endlessly, like a hall of mirrors reflecting the same shape at different magnifications. He called these infinitely repeating structures fractals, and what began as a mathematical curiosity soon revealed a startling possibility. The universe itself might be built this way. Galaxy surveys paint the most striking portrait of this fractal cosmos. If you plot every known galaxy in 3 dimensions, they don't scatter randomly or spread uniformly. Instead, they cluster into filaments and voids, forming a sponge-like structure spanning billions of light years, a structure that looks suspiciously like a neural network or the branching roots of a tree. Zoom in on any single filament and you'll find smaller clusters repeating the same pattern. Zoom in further and the recursion continues. This isn't just visual poetry, it's measurable. When astronomers analyze galaxy distributions, the numbers follow a fractal power law. The number of galaxies in a given volume scales predictably with size, just like the branches of a fern or the tributaries of a river delta. Some analyses suggest this scaling holds for at least 100 million light years, perhaps even farther, but here's where things get controversial. The cosmological principle, a cornerstone of modern astronomy, states that on large enough scales, the universe should look roughly the same everywhere, homogeneous like a well-mixed batter. Fractal patterns challenge that assumption. If matter keeps clustering in self-similar ways ad infinitum, there's no true average density of the cosmos, no smooth backdrop. Instead, reality becomes an endless nesting doll of structure within structure, with no fundamental level where this recursion stops. Proponents argue this explains puzzling observations, like why galaxy rotation curves defy gravity's predictions without invoking dark matter. If mass distributes fractally, its gravitational pull would differ from traditional models. Critics counter that the largest galaxy surveys show homogeneity emerging at the hugest scales, but even that data reveals subtle inhomogeneities, whispers of a deeper fractal order. The implications rewrite our understanding of existence. A fractal universe suggests nature operates by recursive algorithms, where simple rules iterated endlessly generate unfathomable complexity. Picture a cosmic version of the Mandelbrot set, a single mathematical equation repeated, producing an infinite boundary of swirling, self-replicating shapes. Apply this to physics, and the very laws governing atoms might scale up to galaxies or down to quarks. It's already hinted at in quantum mechanics, where particles behave like waves and probabilities branch endlessly. Even time might unfold fractally, with moments repeating in cycles both vast and minute, but the most profound implication, infinity. If the fractal pattern holds, there's no smallest or largest scale, just an endless cascade of structure. Below the Planck length, spacetime might churn with fractal foam. Beyond the observable universe, galaxies could arrange in ever grander versions of the same web. We're left with a haunting question: is the cosmos not just described by fractals, but fundamentally made of them? A single geometric code echoing across the void, weaving everything from quarks to quasars into one infinite, self-similar whole. Time doesn't just move forward, it might flow both ways at once. This is the spine-tingling revelation of time-symmetric quantum mechanics, where the future doesn't just follow the past but actively shapes it. Imagine tossing a stone into a pond and watching the ripples spread outward. Now picture those ripples also converging back toward your hand, as if the splash at the end somehow reached backward to influence the moment the stone left your fingers. In the quantum world, this isn't metaphor, it's math, and it could hold the key to some of physics' deepest puzzles. The proof lies in a series of mind-bending experiments, none more famous than the delayed choice test. Picture a photon racing toward a beam splitter where it can either pass through or reflect, a quantum coin toss. In classic quantum mechanics, the photon remains in a superposition of both states until measured, collapsing into one path upon observation. But what if you wait until the photon has already passed the splitter? Its wave function theoretically committed, before deciding whether to measure which path it took or preserve its wave-like interference pattern. Astonishingly, the results show the photon's behavior changes retroactively, as if the future measurement reaches back in time to dictate whether it behaved as a particle or a wave. It's like a detective altering a crime scene by the mere act of choosing how to investigate it years after the crime occurred. This isn't just quantum weirdness, it hints at a universe where causality isn't a one-way street. In time-symmetric models, particles don't just evolve from past to future, they're equally influenced by boundary conditions in their future. Think of it like solving a maze by working backward from the exit as well as forward from the entrance. Quantum events become two-handed transactions, with handshakes between past and future states determining what happens now. John Wheeler, who first proposed delayed choice experiments, put it poetically: we live in a participatory universe where observation doesn't just record reality but collaborates with it across time. The implications unravel some of quantum theory's knottiest paradoxes. Take entanglement, where particles instantly coordinate states across vast distances. If time is symmetric, their correlation might not require spooky action at a distance, just a mutual connection to a future measurement event that orchestrates their behavior in advance. Even the infamous measurement problem, why observation collapses wave functions, gains new clarity. The collapse could be a negotiation between past quantum states and future outcomes, with the present moment as the meeting point. Skeptics argue this veers into philosophy, but the math holds up. Retrocausal models like the transactional interpretation proposed by physicist Ruth Kastner use time-symmetric equations to predict quantum behavior without the usual ambiguities. Some versions even eliminate the need for parallel universes or hidden variables, offering a cleaner solution to quantum puzzles. And if gravity ever gets a quantum treatment, time symmetry might be the bridge after all. General relativity already treats time as flexible. A photon's path bending near a star isn't so different from its behavior bending toward a future measurement. Of course, this flips our intuition inside out. If the future influences the past, is free will an illusion, or does our present choices still matter? Just as part of a vast two-way causal web, perhaps time isn't an arrow but a tapestry, with every thread pulling equally in both directions. One thing's certain, in a time-symmetric universe, the past isn't just written, it's still being edited by us right now. What if every conscious observer in the universe isn't just witnessing reality, they're actively choosing it? This is the startling claim of the von Neumann-Wigner interpretation, which places consciousness at the center of quantum mechanics, suggesting that the act of observation doesn't merely record reality but fundamentally crystallizes it from a haze of possibilities. Unlike traditional Copenhagen interpretation, where measurement devices collapse wave functions, here it's the mind that makes the final cut. Now weave this into the anthropic principle, the idea that the universe's constants seem eerily fine-tuned for life, and you get the conscious multiverse, a cosmos where observers don't just emerge from the laws of physics, but reciprocally shape those very laws by their existence. Consider Schrödinger's famous cat, suspended between life and death until someone peers into the box. Von Neumann and Wigner took this further. The cat's fate isn't decided by the Geiger counter or the vial of poison, but by the moment a conscious mind registers the outcome. In this view, reality remains a shimmering superposition until awareness steps in, like a director yelling, "Cut," to finalize a scene. The implications ripple outward. If consciousness selects reality, then the universe we perceive might be just one thread in a tapestry of possibilities, chosen because it allows observers like us to exist. This isn't solipsism, it's a participatory universe where life and physics co-create each other. The anthropic principle sharpens the point. Of all possible universes with random physical constants, why do we find ourselves in one where stars burn steadily, atoms bond into molecules, and planets nurture life? The conscious multiverse answers, because only in such a universe could observers arise to ask the question. It's like a cosmic version of the survivor bias. We shouldn't be surprised to live in a habitable universe, since uninhabitable ones have no one to notice their barrenness. But here's the twist: if consciousness truly selects reality, then the very existence of observers might steer quantum outcomes toward configurations that sustain further observation. Life isn't an accident, it's a self-reinforcing loop in the fabric of existence. Experimental hints already nudge this idea from philosophy into physics. In delayed choice quantum eraser experiments, particles seem to know whether their path will be observed in the future, adjusting their past behavior accordingly. If consciousness plays a role, this retrocausality could reflect a universe optimizing itself for observation across time. Even the placebo effect in medicine, where beliefs influence physical outcomes, finds an eerie parallel in a cosmos where mind and matter interweave at the deepest level. Critics dismiss this as mysticism in a lab coat, arguing that consciousness is too ill-defined to anchor a physical theory. Yet proponents counter that dismissing the observer's role leaves quantum mechanics incomplete. After all, every measurement ultimately reaches a conscious mind. Whether the conscious multiverse holds up or not, it forces a profound reckoning. We might not be passive inhabitants of reality, but active participants in its unfolding. And that raises a question as beautiful as it is unsettling. If observation shapes existence, what else might we be choosing into being without even realizing it? Dark energy shouldn't make sense. According to quantum field theory, the vacuum of space should be crackling with enough energy to tear the universe apart billions of times over. Yet when we measure dark energy's actual strength, it's a whisper compared to predictions. This embarrassing mismatch, known as the cosmological constant problem, has haunted physicists for decades. But what if the answer lies in rewriting our understanding of space itself? Enter holographic dark energy, a theory that doesn't just tweak the numbers. It reimagines reality's very fabric. The holographic principle, born from black hole physics, suggests all the information in a volume of space might actually be encoded on its boundary, like a three-dimensional movie projected from a two-dimensional screen. Apply this to dark energy and something remarkable happens. Instead of vacuum energy filling space uniformly, its density becomes tied to the area of the cosmic horizon, the farthest distance light could have traveled since the Big Bang. Suddenly, dark energy isn't a static property of empty space but a dynamic consequence of the universe's information limits. Here's why this solves the cosmological constant problem. Quantum field theory calculates vacuum energy by summing up all possible particle fluctuations in space, an approach that ignores cosmic boundaries. But holographic dark energy imposes a cutoff. The universe can't store more information than what fits on its horizon surface. This cap dramatically reduces the expected energy density, bringing it shockingly close to observed values. It's like realizing your overflowing bathtub isn't leaking. You are just misreading the scale of the container. The math gets even more compelling when you consider time. In this framework, dark energy isn't constant but evolves as the cosmic horizon expands. Early in the universe's history, when the horizon was small, dark energy's effect was negligible. But as space stretched, its influence grew, matching observations that dark energy only recently became dominant. This dynamic behavior sidesteps another headache, the coincidence problem. Why are we alive at the exact cosmic moment when matter and dark energy densities are comparable? Holographic dark energy suggests it's no accident. It's a natural phase in an information-driven cosmos. Critics argue the theory is too speculative, lacking direct experimental proof. Yet tantalizing hints emerge from galaxy surveys. If dark energy's strength varies with the horizon size, its equation of state, a key parameter called W, should deviate slightly from the standard model's prediction of exactly -1. Intriguingly, some measurements of W show a nudge in this direction, though the evidence remains contested. Future projects like the Euclid Space Telescope could settle the debate by mapping dark energy's evolution with unprecedented precision. Beyond equations, holographic dark energy paints a radical new picture of existence. Space isn't just a passive stage for particles, it's an active information network where every cubic light-year's energy depends on what's written at its edges. This isn't just about fixing a calculation, it's about recognizing that the universe might be more like a hologram than we ever dared imagine, where the deepest secrets of reality are tattooed not in its volume but on its skin. The universe isn't just held together by gravity, it's also woven with invisible threads of electricity. This is the bold vision of the plasma universe, where swirling currents of charged particles sculpt galaxies, ignite stars, and stitch the cosmos into a shimmering electromagnetic tapestry. At its heart is plasma, the fourth state of matter, a roiling sea of ions and electrons so energetic they break free from atoms, becoming conductive fluid that responds to magnetic fields like iron filings to a magnet. Nobel laureate Hans Alfvén didn't just study this phenomenon in labs. He saw it as the unseen architect of the cosmos, with filaments of plasma stretching across light years, carrying currents strong enough to power entire galaxies. Picture the cosmic web, that vast network of galaxy clusters and voids spanning the observable universe. Mainstream cosmology attributes its structure to dark matter's gravitational pull, but Alfvén's models suggest another force at work. When plasma moves through magnetic fields, it doesn't flow randomly. It self-organizes into twisting ropes and sheets, precisely mimicking the universe's large-scale structure. In labs, researchers recreate these formations by running high-voltage currents through ionized gas, watching as intricate branching patterns emerge, patterns that uncannily resemble the tendrils of galaxies seen in deep-field telescope images. The resemblance isn't superficial. Plasma's behavior follows well-documented scaling laws, meaning the same physics governing a spark in a lab could operate at galactic scales, just with 1 trillion times more energy. Take solar flares as a microcosm. These eruptions on the sun's surface aren't just hot gas, they're plasma caught in magnetic field lines, snapping like overstretched rubber bands and releasing enough energy to power Earth for millennia. Scale this up, and you get cosmic jets, colossal beams of plasma shooting from galactic cores at near light speed. Traditional models struggle to explain their narrow focus over millions of years, but plasma physics offers an elegant solution. The jets could be pinched by their own magnetic fields, like water squeezed through a hose. Even more compelling, these jets often exhibit helical structures, exactly as predicted when spiraling currents twist plasma into corkscrew shapes. Perhaps the most provocative claim challenges gravity's monopoly on star formation. In standard models, stars are born when gas clouds collapse under their own weight. But interstellar space isn't neutral, it's a plasma peppered with magnetic fields. Alfvén argued that electromagnetic forces could trigger star birth by compressing plasma along cosmic power lines, creating dense knots where gravity later takes over. Supporting this, astronomers now spy stellar nurseries draped along filamentary structures glowing with synchrotron radiation, a telltale sign of electrons spiraling in magnetic fields. Some nebulae even exhibit hourglass shapes eerily reminiscent of plasma Z-pinch experiments, where currents sculpt matter into hourglasses before igniting fusion. Critics dismiss these ideas, citing plasma's low density in intergalactic space. Yet Alfvén's followers counter that even trace ionization allows currents to flow over cosmic distances, just as a nearly empty fluorescent tube still lights up when voltage is applied. They point to enigmatic phenomena like radio loops, gigantic arcs of radio emission spanning our galaxy, as potential evidence of galaxy-scale circuits. Even the mysterious fast radio bursts, brief blasts of energy from deep space, could be cosmic lightning, the snaps of magnetic reconnection in intergalactic plasma. The plasma universe doesn't just reshape how we see the cosmos, it redefines our place within it. We're not passive observers of a gravity-bound clockwork, but inhabitants of an electric firmament, where invisible currents illuminate the dark and magnetism carves paths through the void. Whether this paradigm withstands scrutiny or not, it crackles with a vital reminder. Sometimes, to see the universe anew, we must unlearn the very forces we thought held it together. Every decision you've ever made, every cup of coffee spilled, every whispered confession, every moment of hesitation might have played out in reverse somewhere else, in a universe identical to ours yet fundamentally inverted. This is the startling promise of the CPT-symmetric universe, a theory so elegant it solves two of physics' greatest puzzles in one stroke: the mystery of antimatter's scarcity and the enigma of dark matter's invisible grip. Imagine a cosmos where particles are replaced by their antiparticles, left becomes right, and time flows backward like a film reel spun in reverse. Not as science fiction, but as a legitimate shadow reality woven into the fabric of existence itself. The idea springs from one of physics' most sacred principles, CPT symmetry: charge, parity, and time. Three fundamental symmetries that, when combined, should leave the laws of physics unchanged. Flip a particle's charge c, mirror its spatial coordinates p, and reverse the arrow of time t, and the universe should behave exactly as before. But here's the catch. While individual CP or T violations happen explaining why matter dominates antimatter in our universe, CPT symmetry must hold absolutely. So if our universe violates CP, there must exist a mirror universe where CT is violated to balance the books. A cosmic seesaw where the two realities together preserve perfect symmetry. This mirror realm wouldn't just be a quirky thought experiment. It could be the dark matter we've been hunting for decades. In this model, mirror particles interact with ours almost exclusively through gravity, rendering them invisible to telescopes and particle detectors. They'd form shadow galaxies, shadow stars, even shadow versions of ourselves, living backward from the Big Bang toward some unfathomable beginning, the kicker. Because time runs in reverse there, events in our future influence their past and vice versa. A supernova in their cosmos 10 billion years ago might subtly tug on our galaxy today, explaining dark matter's gravitational fingerprints without invoking exotic particles. Evidence lurks in subtle anomalies. When physicists measured the lifetime of neutrons in bottles versus beams, they found a discrepancy that defies standard models but fits neatly if some neutrons are quantum tunneling into the mirror universe. Even the cosmic microwave background's uneven temperature patches could hint at gravitational handshakes between the two realms, and if colliders like the LHC ever spot particles appearing to vanish mid-detector, they might not be decaying, they could be flipping into mirror space. The implications rewrite reality's rules, entangled particles communicating faster than light, just mirror counterparts coordinating across time's inverted flow. The universe's missing antimatter, it's all there, thriving in a parallel timeline. Dark matter's elusive nature, not a particle at all, but an entire shadow cosmos brushing against ours gravitationally. Critics argue such a universe would leave more detectable traces, but proponents counter that mirror photons and quarks might be just different enough to evade our instruments, like a radio tuned slightly off frequency. Whether the mirror universe exists or not, the theory's brilliance lies in its economy. It doesn't invent new physics, it recycles existing symmetries into a cosmic double exposure, where every star here casts a shadow there, and every ending here is a beginning elsewhere. Maybe dark matter isn't a thing, but a place, an antefloor beneath the universe's feet, holding up the stage we call home. At scales so small they make atoms look like planets, space-time itself might not be smooth and serene, but a chaotic, bubbling froth where reality constantly flickers in and out of existence. This is the quantum foam, a seething ocean of virtual black holes, wormholes, and fluctuations so violent they rewrite the very meaning of empty space. Imagine pouring water into a glass and watching it churn with microscopic whirlpools that vanish as quickly as they form, except here, the whirlpools are temporary black holes and the water is the fabric of the universe itself. The theory traces back to physicist John Wheeler, who realized that quantum mechanics and gravity collide catastrophically at the Planck scale distances of about 10 to the minus 35 meters. At this level, the energy fluctuations predicted by quantum uncertainty become so extreme they warp spacetime into fleeting singularities. One moment, a pinpoint of space swells into a microscopic black hole. The next, it tunnels into a wormhole bridging two distant points. These aren't stable structures but ephemeral blips in reality's code, a foam of possibilities where causality itself stutters. What's astonishing is how this foam might explain one of quantum mechanics' most baffling phenomena, entanglement. When particles become entangled, measuring one instantly determines the state of another, no matter how far apart. In a smooth space-time, this seems impossible, but if the quantum foam is riddled with wormholes, even transient ones, those particles might never truly be separated. Their connection could be written into space-time's turbulent underlay, like two ends of a rope frayed into foam but never fully cut. Recent calculations in string theory and loop quantum gravity support this, showing how entangled particles could share microscopic bridges in the foam, making their coordination less spooky action at a distance and more like neighbors whispering through a porous wall. The foam's wildest implication: it might let us test quantum gravity experimentally. Certain models predict that ultra-high-energy cosmic rays, after traveling billions of light years, should show subtle scattering if spacetime is foamy, like light shimmering on a turbulent pool. Even more thrilling, some physicists speculate that if we could probe the Planck scale, a monumental if, we might catch virtual black holes evaporating via Hawking radiation, their faint death rattles betraying the foam's existence. Others suggest the foam could leave imprints in quantum oscillations of particles trapped in magnetic fields, hints of spacetime's graininess hiding in plain sight. Yet the quantum foam isn't just about untangling physics, it reshapes how we perceive reality. A calm, continuous universe is an illusion. The closer you look, the more spacetime resembles boiling water, with wormholes bubbling up and black holes fizzing away. In this view, the cosmic stage isn't solid but alive, a dynamic scaffold where every point is a doorway, every moment a demolition and reconstruction of existence itself. And if entanglement rides these hidden structures, then the universe isn't just connected, it's stitched together at its most fundamental level, weaving everything from quarks to quasars into a single, shimmering web of foam. What if the universe isn't just governed by fixed laws, but is actively learning them as it evolves? This isn't a metaphor. Some physicists now propose that reality operates like a cosmic neural network, a self-adjusting system where the very rules of physics emerge from a process eerily similar to machine learning. Imagine the universe not as a static rule book, but as a vast, evolving algorithm, tweaking its own parameters over billions of years to stabilize structures like galaxies, atoms, and even life itself. At the heart of this idea lies a surprising parallel between two seemingly unrelated fields, quantum physics and artificial intelligence. In machine learning, neural networks refine their behavior through training, adjusting connection weights between layers to minimize errors. Strikingly, quantum field theory uses a tool called the renormalization group, which describes how physical laws change depending on the scale you're observing. Zoom in on a quark and the strong nuclear force dominates. Zoom out to a galaxy and gravity takes over. This scaling behavior isn't preordained, it's learned, with the universe's fundamental constants acting like tunable weights in a neural network. The cosmos isn't just following laws, it's optimizing them, fine-tuning interactions until they produce stable, complex structures. Consider how a neural network generates images. Start with random noise, then iteratively adjust pixels until recognizable shapes emerge. Now apply that to cosmic evolution. The early universe was a seething plasma of quantum fluctuations, raw noise. Over time, gravity amplified denser regions, galaxies formed, and stars forged heavy elements. This isn't random. It mirrors the way a neural network's latent space organizes data into meaningful patterns. The universe, in this view, is a self-organizing system where the training data is the initial conditions of the Big Bang, and the loss function rewards configurations that persist rather than dissolve into chaos. Even the weirdness of quantum mechanics fits this framework. In machine learning, stochastic gradient descent introduces randomness to escape local optima-suboptimal solutions that seem stable but aren't the best possible. Quantum uncertainty might serve a similar purpose for the universe, injecting randomness to explore different physical solutions until it settles on the stable laws we observe. Entanglement, that could be the cosmic equivalent of backpropagation information feedback, loops that correlate distant parts of the system to maintain coherence. Critics argue this is just an analogy, but the math is tantalizing. Recent papers show that neural networks can rediscover real physical laws from scratch, like deriving the equations of motion from raw data. If a simple AI can uncover Newton's laws, why couldn't the universe itself be running a vastly more sophisticated version of the same process? Some even speculate that dark matter and dark energy are hidden layers in this cosmic network, unobserved parameters shaping the visible universe's behavior from behind the scenes. The implications are staggering. If the universe learns, then the laws we consider immutable might still be evolving. The speed of light, the strength of gravity, these could be variables in a grand optimization process, not fixed constants. Worse yet, what if our universe is just one iteration in a cosmic training cycle, with earlier versions collapsing because their physics didn't permit stable structures? This isn't just reimagining reality, it's turning the cosmos into the ultimate autodidact, a self-teaching system where existence itself is the lesson. And if that's true, the final exam is still ongoing. The Big Bang wasn't the beginning, it might have been the rebound. Picture a cosmic hourglass where the universe doesn't emerge from nothingness but from the explosive aftermath of a collapse. This is the essence of white hole cosmology, a theory flipping black hole physics on its head to rewrite the origin of everything. Unlike their dark counterparts, white holes don't pull matter in, they violently expel it, spewing out energy and space-time like a geyser with no off switch. Now imagine one of these erupting with such fury that it births an entire cosmos. That's the provocative claim of quantum bounce models, where the Big Bang wasn't a singular creation but the spectacular death rattle of a previous universe collapsing into oblivion before bouncing back as a white hole explosion. The math behind this is as elegant as it is mind-bending. When a black hole forms, general relativity predicts its matter crushes into an infinitely dense singularity, a point where physics breaks down. But quantum mechanics abhors infinities, suggesting something must halt the collapse. Loop quantum gravity, one of the leading theories unifying quantum physics and relativity, proposes that at incredibly small scales, spacetime becomes granular, like a woven fabric that can't be stretched or compressed beyond certain limits. As a dying universe contracts, this granularity creates a repulsive force so powerful it reverses the collapse, triggering a rebound. The result, a white hole explosion, a Big Bang reborn from cosmic ashes. What makes this more than just theoretical poetry are the potential observational fingerprints. If our universe began as a white hole, its earliest moments wouldn't have been perfectly smooth. Quantum fluctuations from the pre-bounce phase might have imprinted faint irregularities in the cosmic microwave background, the afterglow of the Big Bang. Some researchers argue these could manifest as unexpected patterns in the polarization of this ancient light, like swirls or anomalies in temperature distribution. Others hunt for gravitational wave echoes, ripples in spacetime from the bounce itself, that could linger in detectors like LIGO or future observatories. Even the universe's large-scale structure might hold clues. A white hole birth could leave subtle asymmetries in how galaxies cluster, a cosmic fingerprint of its explosive origin. Critics point out hurdles. White holes, while mathematically valid in general relativity, require exotic conditions to exist like negative energy or reversed entropy, making them speculative. Yet proponents counter that black holes were once deemed impossible too, until we observed them. The real brilliance of white hole cosmology isn't just its audacity, but its economy. It doesn't invent new physics, it repurposes known laws to erase the need for a miraculous beginning. No singularity, no nothingness before time, just an eternal cycle of collapse and rebirth where every ending seeds a new dawn. Perhaps the most haunting implication is the possibility of cosmic ancestry. If white holes can birth universes, then every black hole in our cosmos might be a wormhole to another spacetime, each with its own laws and constants. Our universe could be one branch on an infinite fractal tree of realities, all linked through gravitational graves. Whether the theory holds or not, it forces us to confront a breathtaking idea. The Big Bang might not have been the first word in creation's story, but the latest verse in an epic poem with no beginning or end. The universe might not run on physics as we know it, but on code. Not metaphorically, not philosophically, but literally. Every photon's path, every quark's spin, every cosmic event could be the output of an unfathomably vast computation unfolding on a grid that spans existence itself. This is the radical vision of digital physics pioneered by computer scientist Edward Fredkin, who saw reality not as smooth and continuous but as a gargantuan cellular automaton. Think Conway's game of life, but with rules complex enough to generate everything from supernova to human thought. Picture the cosmos as a cosmic chessboard where each square isn't just a passive pixel but an active processor, crunching simple rules to birth infinite complexity. Fredkin's hypothesis turns traditional physics inside out. Instead of matter and energy being fundamental, they are emergent properties of information processing. Space isn't an empty stage, it's a lattice of discrete cells, each holding a finite amount of data. Time isn't a flow but a series of computational ticks, like the clock cycles of a computer. Even particles aren't tiny billiard balls but stable patterns gliding across this grid. Their interactions dictated by local rules no more mysterious than the logic that makes gliders zip across a game of life board. The kicker, this isn't just abstraction. Certain quantum behaviors like entanglement and superposition make bizarre sense if you view them as features of a universe running on distributed computation. Take the double-slit experiment where particles act as both waves and particles until measured. In a cellular automaton, this wave function collapse could simply be the system resolving an undetermined state into a definite output once information reaches a threshold, like a pixel updating its color based on neighboring cells. Even the speed of light finds an elegant explanation. It's the maximum rate information can propagate across the grid, just as no signal in Conway's game of life can travel faster than one cell per generation. Critics argue this reduces the richness of nature to cold calculation, yet digital physics counters that complexity emerges from simplicity. The Mandelbrot set springs from a one-line equation. Could the universe's laws be similarly concise algorithms? Strikingly, some formulations of quantum mechanics already treat particles as information packets. Their properties defined by binary yes/no questions qubits rather than tangible substance. Even black hole thermodynamics, where entropy scales with surface area, hints that reality might store data on boundaries, not volumes, just like a cellular automaton's next state depends solely on its perimeter cells. The most provocative implication: if the universe computes itself, it might be possible to hack the code. Fredkin speculated that advanced civilizations could one day manipulate the grid's rules, rewriting physics locally like programmers tweaking a simulation. Wild as it sounds, lab experiments already simulate quantum systems on small-scale grids, and theories like loop quantum gravity treat spacetime as a network of discrete grains. Perhaps we're not just players in the universe's game, but potential co-authors of its next patch. What clinches the theory's audacity is its testability. If spacetime is a lattice, high-energy particles like cosmic rays should stumble upon its graininess, deviating subtly from predicted paths, an effect some observatories are actively hunting. Others search for anomalies in the cosmic microwave background that could betray the grid's resolution. Whether digital physics holds up or not, it forces a profound shift. The universe isn't just described by math, it might be math humming along in an endless loop of self-updating code. And that raises a chilling question. If reality runs on computation, who or what wrote the program? What if the universe doesn't exist unless you're looking at it? This is the heart-stopping premise of biocentrism, a theory championed by scientist Robert Lanza that flips reality on its head. Instead of consciousness emerging from the machinery of the brain, Lanza proposes the opposite, that consciousness is the fundamental fabric of existence, and the cosmos we perceive is merely its byproduct. It's not that life evolved to comprehend the universe evolved to be comprehended by life. At its core, biocentrism doesn't just challenge our place in reality, it rewrites the script entirely, suggesting that without observation, the universe remains an unrealized potential, a cosmic rough draft waiting for a reader. Quantum mechanics offers startling support for this idea. Take the double-slit experiment where particles behave as waves until measured, then abruptly choose a definite state. In a traditional framework, this is puzzling. Why should observation change physical behavior? But biocentrism reframes it. The particle isn't being measured into existence, it's being actualized by the conscious act of observation. The universe isn't a pre-existing stage, it's a dynamic performance where consciousness is both the audience and the director. Even more provocative, quantum entanglement, where particles instantaneously coordinate across vast distances, makes eerie sense if reality is a construct of interconnected awareness, with no true separation between observer and observed. Lanza extends this logic to cosmology. Why do the laws of physics seem exquisitely fine-tuned for life? The anthropic principle argues it's because we couldn't exist otherwise. Biocentrism goes further. Those laws aren't accidents but artifacts of consciousness itself. Space and time aren't absolute containers but tools forged by perception, like the operating system of a cosmic computer running on mindful input. Think of a video game rendering graphics only where the player looks, except here, the player is any conscious being, and the graphics include stars, planets, and the very fabric of space-time. Critics dismiss this as solipsism dressed in quantum jargon, but biocentrism counters with empirical puzzles. Why does the brain process sensory input milliseconds before stimuli occur in experiments on backward time referral? How do placebo effects sometimes override biochemistry? These anomalies hint at a universe where mind isn't trapped in the skull but interwoven with matter, shaping it as much as it's shaped. Even near-death experiences, where patients report vivid awareness during clinical brain death, suggest consciousness might not be confined to neural activity at all. The implications are staggering. If biocentrism holds, death might be less an end than a transition, a shift from one perceptual framework to another, like closing one eye to open another in a multiverse of observer-dependent realities. The theory doesn't just elevate life's role in the cosmos, it makes life the raison d'etre for the cosmos. Whether proven or not, biocentrism forces a reckoning. We're not just bystanders in an indifferent universe. We might be its architects, dreaming the world into being with every thought, glance, and question. And if that's true, the greatest mystery isn't out there in the stars, it's the unexamined power of the mind gazing at them. Imagine two entangled particles, electrons spinning in perfect sync across the galaxy, instantly mirroring each other's states no matter the distance. This spooky action at a distance baffled even Einstein, but what if the answer isn't some invisible signal, but a hidden tunnel stitching space itself together? Enter the holographic wormhole universe, a theory so audacious it merges two of physics' wildest ideas, the holographic principle and the ER=EPR conjecture. The result, a cosmos where every quantum entanglement is a microscopic wormhole, threading through the quantum foam like invisible strands in a cosmic tapestry. The holographic principle, as we've seen, suggests that all the information in a volume of space, every star, every atom, every thought, is encoded on its boundary, like a three-dimensional movie projected from a two-dimensional screen. But in 2013, physicists Leonard Susskind and Juan Maldacena took this further with their ER=EPR proposal. The shorthand refers to two landmark papers. Einstein and Rosen's work on wormholes, hypothetical bridges through spacetime, and Einstein, Podolsky, and Rosen's paper on quantum entanglement. The radical claim these aren't separate phenomena. Entangled particles aren't just mysteriously linked. They're literally connected by wormholes too tiny to see, threading through the frothy quantum vacuum. Picture space-time at the smallest scales not as smooth and serene, but as a turbulent foam of virtual black holes and wormholes flickering in and out of existence. In this seething quantum sea, every time particles become entangled, a microscopic wormhole forms between them, a tunnel so minuscule it's imperceptible, yet binding them as surely as a hidden umbilical cord. This isn't just poetic metaphor. The math reveals that the equations describing entangled particles are eerily similar to those governing wormholes' geometry. It's as if the universe has been whispering the connection all along, hidden in the scribbles of general relativity and quantum field theory. Why does this matter? For one, it could solve the black hole information paradox, the puzzle of what happens to information swallowed by a black hole. If entanglement is wormhole-mediated, then information isn't lost, it's just rerouted like a letter slipping through a secret postal network. Even more tantalizing, it suggests that space itself might be built from entanglement. Just as threads weave fabric, entangled particles, linked by wormholes, could stitch together the very structure of spacetime. This means the distance between stars or galaxies isn't fundamental. It emerges from a deeper, interconnected network of quantum ties, but the wildest implication. The holographic wormhole universe blurs the line between the very large and the very small. A black hole's event horizon, a boundary so vast it warps galaxies, could be entangled with particles inside it, their connection a wormhole in disguise. Scale this up, and the entire cosmos might be a web of entanglement, with wormholes threading every atom to every star, every thought to the edge of reality. The universe wouldn't just be holographic, it'd be a living, breathing network of hidden tunnels where every quantum handshake is a secret passageway and empty space is anything but. Of course, skeptics demand evidence. If wormholes lace the quantum foam, could we ever detect them? Some theorists propose hunting for anomalies in particle collisions, tiny deviations that betray a wormhole's brief existence. Others suggest that entangled systems in labs might exhibit subtle geometric signatures, like extra dimensions curling around their connection. And if the theory holds, it would mean that every time you measure an entangled particle, you're not just observing a distant partner, you're peering through a wormhole to touch it across space and time. The holographic wormhole universe doesn't just redefine entanglement, it reimagines reality's scaffolding. Space-time isn't a static stage, it's a dynamic mesh of quantum threads where every connection is a wormhole and every observation tugs on the web. From black holes to quarks, the cosmos might not be a collection of objects but a constellation of tunnels, a universe where nothing is ever truly separate, just hidden by folds too small to see. Time's relentless march forward, the melting of ice, the fading of stars, the fading of memories feels as undeniable as gravity. But what if this arrow of time isn't written into the universe's fundamental laws? What if it's just thermodynamics playing out on the grandest stage, a cosmic game of energy dispersal where the entire structure of reality emerges from the simple drive toward maximum entropy? This is the heart of the thermodynamic universe theory, a framework where black holes, information, and the very fabric of causality might all be threads woven from the same deep principle, the universe's unshakable urge to spread energy as evenly as possible. Start with a cup of coffee, pour cold milk into it, and watch as the two liquids mix effortlessly. Yet no matter how long you wait, they never spontaneously separate again. This everyday phenomenon captures entropy's essence. Systems evolve from order to disorder, never the reverse, but zoom out to cosmic scales and the plot thickens. The early universe was a scorching, nearly uniform soup of particles, a state of astonishingly low entropy. Over billions of years, gravity amplified tiny fluctuations, sculpting galaxies and stars from this smooth beginning. Paradoxically, gravity creates structure clumps of matter while driving the universe toward higher overall entropy. A star, for instance, seems ordered, but its nuclear fusion scatters energy into space far more efficiently than a cold cloud of gas ever could. In this light, the cosmos isn't defying thermodynamics, it's fulfilling it, using gravity as its paintbrush to spread energy across the void. Now bring black holes into the picture. These gravitational monsters are entropy powerhouses. A single black hole's event horizon encodes more entropy than all the stars and gas in the visible universe combined. When Stephen Hawking discovered that black holes emit radiation and slowly evaporate, he stumbled upon a shocking truth. They're the ultimate thermal engines, converting mass into heat with perfect efficiency. But here's the twist: if black holes maximize entropy, what happens to the information swallowed by them? The infamous black hole information paradox arises because quantum mechanics insists information can't be destroyed, yet general relativity claims it vanishes forever behind the event horizon. The thermodynamic universe framework offers a daring solution. The information isn't lost, it's scrambled into the black hole's Hawking radiation, like a message hidden in the static of a radio. This way, entropy keeps increasing and the universe's accounting stays balanced. The implications spiral outward. If black holes are entropy's ultimate expression, then the arrow of time itself might be their doing. Some theorists propose that without black holes, without these cosmic mixers churning order into disorder, time's flow would lose its direction. Even more radical is the notion that space-time itself could emerge from thermodynamic principles, like temperature differences generating weather patterns. In this view, the Einstein equations governing gravity might not be fundamental laws, but emergent ones, statistical tendencies arising from countless microscopic degrees of freedom, the same way pressure emerges from atoms bouncing in a gas. So where does this leave us? Staring into the abyss of heat death, the universe's final state where entropy maxes out and all energy is evenly distributed. No stars, no life, no gradients, just a lukewarm sea of photons drifting endlessly. Yet even here, the thermodynamic universe theory whispers a tantalizing possibility. Quantum fluctuations in this void could, given infinite time, spawn new low-entropy bubble seeds of fresh cosmic cycles. Our universe's story might not be a one-way ticket to oblivion, but a single chapter in an epic where time's arrow is just a symptom of thermodynamics' grand, unyielding dance. Every reality we perceive, the solidity of tables, the certainty of sunrises, even the continuity of our own thoughts, might be nothing more than a consensus hallucination, an illusion carved from quantum chaos by the relentless scrutiny of the environment itself. This is the unsettling premise of quantum Darwinism, a theory that reshapes how we understand the transition from the blurry quantum realm to the crisp classical world we experience daily. Picture a quantum particle existing in multiple states at once, like Schrödinger's infamous cat, both alive and dead. Now imagine the environment, every photon, air molecule, or stray electron nearby as an audience, constantly voting on which state becomes real by interacting with it. Over time, only the most resilient states survive this Darwinian selection, while others fade into oblivion. What we call objective reality isn't fundamental. It's the last theory standing after nature's endless elimination round. The magic lies in a process called quantum decoherence. When a particle's wave function interacts with its surroundings, its fragile superposition of states collapses into a single, definite outcome. But here's the twist. Decoherence doesn't just erase quantum possibilities, it amplifies certain states by making them repeatable. Think of a drop of ink in a glass of water. At first, the ink forms intricate, swirling patterns, but over time it spreads uniformly. The environment, the water molecules, doesn't care about the ink's initial artistry. it relentlessly pushes the system toward a stable, predictable state. Similarly, quantum systems leak information into their surroundings, and only states robust enough to leave multiple, redundant imprints endure. These imprints become the shared reality observed by countless interactions, like a viral meme spreading until it's unavoidable. Experiments have caught this process in action. In labs, delicate quantum superpositions of particles last microseconds until even the faintest disturbance from the environment breaks the spell. But the real clincher comes from quantum dots, tiny semiconductor structures where electrons exist in superpositions. When researchers measure these systems, they don't see all possible states equally. Instead, certain configurations dominate precisely because they've been chosen by relentless environmental interactions. It's as if reality isn't dictated by a single measurement but by a chorus of tiny observers, none conscious but all collectively shaping what we perceive. Quantum Darwinism doesn't just explain why we see tables and chairs instead of quantum fog. It redefines what seeing even means. Your eyes don't passively detect light. They participate in a feedback loop where photons from an object have already been pre-selected by countless prior interactions. The tree falling in the forest does make a sound, but only because the air, leaves, and ground have already cast their votes on how vibrations should propagate. Even time's arrow might emerge from this process. As decoherence spreads information irreversibly into the environment, it creates the one-way flow we experience as causality. Critics argue this merely kicks the can down the road. What determines which states are fittest to survive? The answer might lie in symmetry and stability. States that align with conserved quantities like energy or momentum resist decoherence, much like evolutionary adaptations that fit ecological niches. Others suggest Darwinism's true test will come at the edge of quantum gravity, where spacetime itself may decohere into classical geometry. Yet the theory's elegance is undeniable. It turns the observer's role on its head. We're not special, just latecomers to a reality shaped by trillions of mundane interactions before we ever looked. The most profound implication: reality isn't a static stage. It's a dynamic negotiation where the quantum and classical worlds aren't separate realms but phases in an endless selection process. What we call the laws of physics might just be the habits of a universe that's learned through endless trial and error how to be consistent. And if that's true, then every solid object, every sunrise, every thought you hold as real is less a fundamental truth and more a quantum survivor, a fleeting consensus in an ocean of possibilities. Numbers don't just describe reality, they might be reality. This is the startling claim of Max Tegmark's mathematical universe hypothesis, a theory so audacious it reduces everything, every galaxy, every thought, every law of physics, to a single, inescapable truth. If something can exist mathematically, it does exist physically. No abstractions, no metaphors, just pure, unfiltered math manifesting as the cosmos. Imagine every possible equation, every geometric shape, every logical structure playing out somewhere in a multiverse so vast it makes parallel universes look quaint. Our universe isn't special. It's just one page in an infinite textbook of mathematical possibilities, where even the most alien geometries and unthinkable physics become somebody's version of home. Tegmark's reasoning begins with a simple but radical observation. Mathematics isn't something humans invented, it's something we discovered. The Pythagorean theorem was true long before Pythagoras drew his first triangle, and the Fibonacci sequence unfolded in sunflowers and galaxies before anyone named it. This suggests math exists independently of minds, like a landscape waiting to be explored. Now take this further. If a mathematical structure is internally consistent, if its rules don't contradict, why shouldn't it correspond to a physical reality? In this view, the universe isn't described by math. It is math with particles and forces, just shadows of deeper numerical relationships. Consider how we already treat physics. An electron isn't a tiny ball but a probability cloud defined by wave functions, pure mathematical objects. Space-time bends according to Einstein's equations, not because it obeys them, but because it is them. Tegmark argues this isn't coincidence but clue. Reality doesn't run on math, it is math, and we're just patterns within it. Think of Minecraft's blocky world, where every mountain and tree is ultimately made of code. Our universe might be no different, with atoms and energy as tokens in a cosmic calculation. But here's where it gets wild. If every consistent mathematical structure exists physically, then universes with different dimensions, forces, or even logics must be out there. Some might have 7 spatial dimensions, others with time that loops like a DVD menu screen. There could be worlds where gravity repels, where circles have corners, or where numbers behave so bizarrely that physics as we know it is unrecognizable. Our cosmos, with its 3 spatial dimensions and quantum fields, isn't the rule, it's one arbitrary line item in a multiverse of equations. Critics argue this is untestable metaphysics, but Tegmark counters with 2 challenges. First, if math is all there is, why does our particular universe seem so finely tuned for life? His answer: survivorship bias. We couldn't exist in the vast majority of mathematical structures. Try living in a universe that's just a prime number, so we're naturally in one of the rare, hospitable ones. Second, he points to the unreasonable effectiveness of mathematics in science. Why should scribbles on a chalkboard predict black holes or quantum particles unless they're tapping into something fundamental? The most mind-bending implication: consciousness itself might be a mathematical pattern. If thoughts are just information processing, then any sufficiently complex computation, whether in neurons or silicon, could spawn subjective experience. In this view, you're not a ghost in the machine, you are the machine, a self-aware knot of equations in a cosmic proof. Whether Tegmark's hypothesis holds or not, it forces a profound question. Are we explorers in a mathematical universe, or are we the math itself awakening to its own existence? From colliding universes birthing our own in a fiery cosmic rebound, to entire realities nested inside black holes like cosmic Russian dolls, we've ventured through theories that don't just push the boundaries of science but shatter them entirely. Whether it's the holographic universe suggesting we're all projections on a distant 2-dimensional surface, or the Boltzmann brain paradox whispering that your memories might be nothing more than a random fluctuation in the void, each idea forces us to confront the same unnerving question: how much of reality can we truly trust? These theories aren't just academic exercises, they're tectonic shifts in how we understand existence. If space-time is a quantum foam riddled with wormholes, then entanglement isn't magic, it's geometry. If consciousness isn't confined to brains but woven into the fabric of the cosmos, then the universe isn't just aware, it's alive in ways we can barely fathom. And if we're living in a simulation, a mathematical structure, or one branch of an infinite multiverse, then the very meaning of real dissolves into something far stranger and more malleable than we ever imagined. Yet amid the chaos of competing ideas, one truth emerges: the universe is nowhere near as settled as we once believed. Every answer spawns deeper questions, every discovery reveals new layers of mystery. And that's the beauty of it. Science isn't about carving truths in stone. It's about chasing the next revelation, even when it upends everything we thought we knew. So which theory bends your mind the most? Do you find yourself drawn to the elegant brutality of the Big Rip, or the haunting recursion of Penrose's cyclic cosmology? Maybe the participatory universe, where observation shapes reality, feels less like physics and more like philosophy. But then again, the line between the two has always been blurrier than we admit. Drop your thoughts in the comments. This isn't just a one-way conversation. The cosmos is too vast, too weird to explore alone. And stay tuned, because beyond these 30 theories lie even wilder frontiers. From the quantum echoes of other dimensions to the possibility that time itself is an illusion, The universe's greatest secrets are still waiting to be uncovered. The rabbit hole doesn't end here, it goes deep.